Now that we know our orientation of our periodic table, our groups, our periods, we know that's laid out based on atomic number. We know that the groups have similar chemical and physical properties because of their electron configurations and how they react. Well, now, if we look at it as a whole group, we can pick out some trends of reactivity on the periodic table. So we're going to look at these you know what? We'll add a fifth. We're going to look at ionic radii as well. So electron affinity, ionization energy, atomic radii, electronegativity, and ionic radii. Really quickly here. Okay, so the first trend we're looking at is we're looking at electron affinity. And what electron affinity is exactly what it sounds like. It is the affinity an element has for another electron. So when we add an electron to a neutral element, there's just my element here, we're adding an electron. What happens is when we add an electron to an element, to a neutral element, energy, in most cases, is released, even with our metals, which we wouldn't typically expect. But if we add electrons to neutral elements, energy is released. So our electron affinity is the amount of energy that is released. Now, most of the times it is listed as a negative value because that energy is leaving the atom. So it's entering the world, it is leaving the atom. So if we add an electron, energy is released. I'll write out energy, and that is the electron affinity. So what we'll notice by this trend is as we get closer and closer to the noble gas state, and actually noble gases tend not to have electron affinities because they already have a stable electron configuration. But notice as we add electrons to elements and they get closer and closer to a noble gas state, they have an increasing electron affinity. So they have more pull on that free electron that we're adding to it. They release more energy when we give it. Now notice this trend makes sense, right? As we go from left to right, the electron affinity is increasing as we get closer and closer to a noble gas state. The other trend, though, is we see it increases as we go up the periodic table. So fluorine would be our element with our highest electron affinity. Now, the reason why there is that fluorine is just smaller, so that electron can get closer to its nucleus. Imagine fluorine here with really two shells of electrons, as opposed to iodine, that has 1, 2, 3, 4. It's in the fifth energy level, so 1, 2, 3, 4. Now, iodine also really wants that electron, but it has all these layers of electrons that provides what we call shielding. So it shields the nucleus from that electron that we're trying to add, so it has a lower electron affinity than fluorine. So it increases as we go up because the element is smaller, there's less shielding. It increases from left to right as we're filling that octet. Now, this trend isn't completely perfect. What we'll see is there are some hiccups. And notice what this has is this has the values as positive values. Typically, they're going to be listed as negative because this energy is going to be released from the atom. So the atom itself is going to go down in energy. It is in exothermic reaction. It is releasing that energy. So notice what we have. We have an electron affinity. Even for hydrogen, adding an electron to hydrogen, it releases energy. But notice it drops to helium. So we just said that trend increased from left to right, but now we're showing that there's some hiccups in there, okay? So helium, because it has a full S shell, actually is very stable and has almost zero electron affinity. Now notice as we start at lithium, which is our group 2, lithium is higher, beryllium drops, up to boron, up to carbon, and now drops at nitrogen. Nitrogen has a very, very low electron affinity. Now, why might that be? Well, if I pull out my pocket periodic table I keep over here, let's take a look at where nitrogen is. Notice nitrogen, again, is halfway through the p block, so again, it's paramagnetic. So again, when we have that half-full shell, there's some level of stability, and we can see that in the electron affinity. So after we get by nitrogen, then notice it picks up again, increases to oxygen, increases way up when we get to our halogens because they're right close to an octet. They can, if they gain just one more electron, they're going to have an octet. They're going to be very stable. And notice again what happens to the electron affinity when we get to our noble gases. Drops off to basically our zero value. Notice we start that same trend again. Sodium down to magnesium because that's a full S shell, aluminum, silicon, and now notice phosphorus again. So these are those repeating physical and chemical properties we are talking about that we see. Things like electron affinity. We see the same repetition across our groups and our periods. So when we look at the periodic table, we're going to see those trends repeating and repeating. So nitrogen, again, has a 0 electron affinity. Phosphorus is pretty low. We'll probably see the same thing with arsenic because they're all in the same group. They all have a half-full p shell, and so they have some relative stability. Again, all of our noble gases have an electron affinity near 0 because they are very stable. They have no need for another electron. And again, we see a slightly lower electron affinity with our alkali earth metals because they have a full S shell. But again, our general trend is from left to right, increasing towards fluorine. That's typically good enough to know that that's our general trend, but we do want to remember that noble gases do not have an affinity for electrons. And if you're paramagnetic or have a full S shell, your affinity is going to be slightly lower than what would be predicted. One more little graph to look at. Notice these are some numbers formed. Notice our alkali earth metals with these 0 values. Same thing with our noble gases. Nitrogen, very low. Phosphorus is smaller, but it does have a slight electron affinity. But what we can see is this big jump at our halogens. But again, notice it goes down as we go down the group because, again, the element is getting bigger and it gets harder and harder to attract that extra electron. So if the electron affinity was the amount of energy released when we added an electron, ionization energy we can think of as the opposite. That's the amount of energy it takes to rip an electron out. So if we want to remove an electron, guess what? We need to add energy to that atom to kick that electron out. That is ionization energy. And what we'll see, same trend as we saw for affinity. So for electron affinity, things wanted more electrons as we got up and up closer to fluorine. Well, the same general trend is true for ionization energy. If things have stronger affinity for electrons and release more energy when we give them electrons, they're going to be the same elements that are going to be very hard to take electrons away from. So notice from left to right, because that energy level is filling, we're getting closer to an octet. And from bottom to top, because again, these are smaller elements, so there's less shielding, and it's going to be harder and harder to take electrons away from. So notice big elements, especially big elements with few outside electrons, are going to be really, really easy to take electrons away from because those electrons are very far from the nucleus and they only have a few of them. So we see a similar type of pattern now when we look at ionization energy. Again, ionization energy is a positive value because this is energy we need to put in to remove just one electron, so it's first electron. Now there are second and third ionization energies, but for the most part we're just going to focus on removing just one electron. So notice hydrogen is a pretty high number, but then helium goes way, way up. Look how high the ionization energy is for helium. And notice helium and all of our noble gases have ionization energies. So it is possible to remove electrons from them, but very, very, very difficult to do. So helium is very high. Notice we dropped lithium, an alkali earth metal. Easy to remove electron because it only has one in its outside orbit. Go up to beryllium, drops a little bit to boron, right? Now notice, why is that? Well, notice, again, beryllium has a full S shell, so it's going to be a little bit harder to remove an electron from beryllium than boron that just has one in its p block. Notice, if we look down on this small diagram down here, there is a slight peak in ionization energy at nitrogen because, again, it is slightly more stable than the elements around it because it's paramagnetic, and then it goes up, up, up until we have that huge peak at neon. So unlike electron affinities, noble gases did not have a pull on electrons, but they're very, very hard to remove them from. But again, notice the general trend that as we go down the table, as we go down, the ionization energy decreases. And again, that is just because the element is getting much, much larger. There's more shielding, so there's easier to remove those outside electrons. Now, our next trend, atomic radii. And this is the one that I think people get. It's easy to think that, okay, as you get closer to an octet, and as you get smaller, you have a stronger pull on electrons, so you're going to have a higher electron affinity, and you're going to have a higher ionization energy. But the one people get wrong a lot is increasing atomic radii, the radius or radii. How this is measured is this is actually measured based upon half the bond length when the element is bonded to itself. So it's very difficult to measure individual atoms floating around, but bond lengths can be measured. And then the atomic radii is half that bond length when the element is bonding to itself. That's the standard definition for it. Now notice how it increases. It increases going down, so elements get bigger as we go down the periodic table, which should make sense, because notice we're adding energy levels. Energy level 1, energy level 2, 3, 4, 5, 6, 7. So we're adding energy levels, so it makes sense that as we add stuff, it gets bigger. What confuses a lot of people is that the element is actually bigger from right to left. So as we add electrons going across this way, the element actually gets smaller. The reason why is we're adding electrons and protons into the same energy level. So as we add stuff across energy level 2, we're adding stuff all in the same energy level. So the effective nuclear charge, we're adding more electrons, but you have to think we're also adding more protons. So the effective nuclear charge on those electrons increases and pulls everything tighter together. So again, this is the trend that people kind of struggle on, but if we look at this graph, here's what we'll see. So notice our alkaline metals tend to be our biggest elements, and again, their size increases as we add energy levels, as we go down the periodic table. Now, as we add electrons in that energy level, the element gets smaller and smaller because what we call the effective nuclear charge increases, again, until we get to our noble gases, which we consider our smallest elements. Then there's a huge, huge peak to sodium. So between neon and sodium, so as we go from right here, neon, to have a full outer shell, very small element, now we go down a row to sodium, and there's a huge, huge, in terms of atoms, jump in atomic radii. That is because to go to sodium, we have to add a whole nother energy level. So that energy level is completely full, the second energy level, and we are now down into the third energy level. And when we add that whole other energy level, we only have one electron in it, and it can venture very far from the nucleus. Again, until we start adding protons and electrons to that nucleus, and then our elements get smaller and smaller. Again, notice there's not as much disruption in that trend as we've seen in our other trends. Notice there is when we get into our transition metals, but our transition metals are a little hairy. There's a lot going on there. They get a little bit messy as far as talking about atomic radii. We aren't going to focus on all those kind of differences in the transition metals, only, again, the general trend, which, again, we can see on this diagram as well. So we see here our biggest element is cesium, again, because it has a lot of energy levels and only one electron in its outside orbit. As we add stuff to that energy level, the effective nuclear charge increases, holding everything tighter together. So right now, this is a summary of what we've looked at so far. So atomic radii increases down to cesium, would be what we consider, or francium, we would consider our largest element if we add in francium. No ionization energy at electron affinity increase towards our halogens, or for ionization energy, even towards helium. And notice one other thing we're putting on this graph is the non-metallic or metallic character. So our biggest elements are going to be the most metallic. So elements on this side of the periodic table, on the left side of the periodic table, and again, we could cut our periodic table down the zigzag line here. We've talked about that just a little bit. Elements to the left are called metals. And actually, as we get further from that zigzag line, we see more of what we call metallic character. If we go to the other side of the zigzag line, we have nonmetals, and actually the further we get, the more non-metallic character we have. That's going to be important as we go a little bit further on. Now, what we're going to look at now is electronegativity. Electronegativity is very, very similar to electron affinity because it's all about the pull on an electron. But electronegativity is slightly different. It's the pull on the electron within a bond. So not just a pull on an electron floating around, but a pull on an electron within a bond. However, we see the same trend as we see for electron affinity. Notice here's some values, and notice these values don't have units on them. They're not in like kilojoules per mole, because these are really not as quantitatively based. These are based on looking at bond strengths and looking at polarity of bonds. So it's a little bit different. It's a little bit more theoretically derived than some of our other numbers that can be directly derived. So notice the general increase, though, up towards fluorine. Again, noble gases don't have electronegativities because they have 8 electrons in their outside orbit. They're already fairly stable. Notice we see some of the little bumps within trends, especially in our transition metals, but our general trend goes up to fluorine. Now, what we're really going to use is a table like this. And what this table is going to allow us to do is predict, as we go forward into the next chapters, what type of bonding we're going to see. Because things that have high electronegativity values like fluorine, well, they tend to actually remove electrons. If your electronegativity value is high enough, Well, you can remove an electron for something that has a really low electronegativity, like, say, francium. So if we have electronegativity of 4, that is saying, and all these elements are actually based off of the electronegativity of fluorine because it's our strongest. If you have electronegativity of 4, you have a big likelihood of removing the electron and becoming a negative ion, becoming an anion. If you have a really low electronegativity like francium, well, you have a high probability of losing that electron to an anion, becoming positively charged. So what we see here, based on electronegativity, is again, if we cut the periodic table down right here, what we'll see is things up here that are our nonmetals. Well, our nonmetals tend to have high electronegativities, and thus they tend to gain electrons, and they tend to form anions. Our metals are opposite. They tend to have electronegativities below 2, pretty low. And so what they'll do is our metals tend to lose electrons, and they'll form cations, or positive ions. And how many they lose really is dependent upon their place on the periodic table. So notice fluorine is 1 away from having an octet. Fluorine tends to gain 1 electron, get a -1 charge. Oxygen, sulfur, selenium tend to gain 2 electrons because they're 2 electrons away from having a noble gas state. Nitrogen, phosphorus tend to gain 3. Carbon or silicon can actually gain or lose electrons because they're kind of in the middle, and they tend to actually not really gain or lose electrons very often. They tend to form actually sharing covalent bonds, but we'll get to that later. So we tend not to see ions actually very often with carbon. We can see -4 charged ions for carbon, but that's more rare. When we go to the metal side now, they tend to lose electrons. So hydrogen and all the alkali metals tend to be +1 ions in bonds. They lose 1 electron. Magnesium, calcium, beryllium tend to be +2 ions in bonds. So we can predict how these things will react, how they'll form bonds, how many electrons they'll either gain or lose. Again, all of these tend to gain electrons to get to an octet. All of these tend to lose electrons to get to an octet. Metals lose electrons, nonmetals gain those electrons. And again, how many they gain or lose can be predicted from their place on the periodic table. And we can even predict the charge on our transition metals. It takes a little bit more work, but again, as we go into the bonding chapter, we'll discuss that. So what's going to happen to our elements as they gain or lose electrons? Well, let's look at 2 examples, sodium and chlorine, that react to form sodium chloride. Well, sodium, notice, is right here, is in the first, it's in the 3rd energy level, but group 1. So it has 1 outside electron, so it is going to tend to lose 1 electron and form a +1 ion. So that is what this diagram, this Bohr diagram is showing us, is sodium has 11 protons, it has 11 electrons in a neutral element, but it only has that 1 outside electron. That 1 outside electron actually is very far from the nucleus because it tends to be a big element within its energy level, and so it's going to tend to lose that 1 electron. Well, where can it lose it to? Well, it can lose it to a chlorine, because let's look at where chlorine is on the periodic table. Chlorine is in the same period, but on the opposite side. So it has 7 valence electrons, so it's going to gain 1 electron to get to a noble gas state. So it wants to gain 1 because, let's look, it has 1, 2, 3, 4, 5, 6, 7 outside electrons. 17 total, but again, we don't really care as much about the total as we care about the outside electrons, the S and P electrons. That's going to determine how it reacts. So it has a place to accept 1 electron. And so guess what? If it's next to sodium, it will accept 1 electron. This will get 18 electrons, 17 protons, have an overall net charge of -1. Sodium will lose it, have an overall charge of +1, and then those 2 things will stick together in what we're going to call an ionic bond. This will be a +1, and it will bond to chlorine with its -1 charge. But really, they are both more stable, because now both of them actually have a noble gas electron configuration. Chlorine gained 1, now it has an electron configuration of krypton. Sodium lost it, now it has an electron configuration of neon. And when it has that, even though it's an ion, it is actually a more stable element in that formation. Now the other thing we want to know is what happens to the size of these elements when these things react. Well, that part's pretty easy. If you lose an electron, just like this diagram shows, you get smaller. If you gain an electron, like this diagram tries to show, but it's kind of hard to illustrate, it actually gets bigger. So if we look at our ionic radii, and this is a comparison of atomic to ionic radii, Notice if you lose electrons, this is the normal size of lithium, loses its electrons, it gets much smaller. If you lose 2 electrons, you get even smaller. If you lose 3 electrons, that's a lot of electrons to lose. So as you lose electrons, that ion gets smaller. On the opposite side, so again, these are all metal ions that tend to lose electrons and form cation ions. And again, the number they tend to lose is based on what group they're in. Group 1, notice they all have a +1 charge because they tend to lose 1 electron. Group 2 elements all have a +2 charge because they tend to lose 2 electrons. And notice the red color, or the blue color here is their original size, or purple. You can disagree with me on color. The gray is what they are as an ion. On the opposite side, we have nonmetals that tend to gain electrons. And again, the number they gain is dependent upon what place they are on the periodic table. Group 7 tend to gain 1. Notice they are getting bigger when they gain 1. Group 2 tend to gain 2. In fact, it's a lot bigger when they gain 2 electrons. Group 3 gets bigger as they gain 3 electrons. So here's a nice chart that's a summary of all of those trends. Again, elements, where they are on the periodic table, tells us a lot about how they're going to chemically react and how they're going to form bonds. So what we want to do is know these trends, be able to predict those sizes, the electron activities, the ionization energies, so that we can predict how these things are chemically going to react and how they're going to combine chemically in bonds, which is our next chapter or section or unit that we're looking at after electrons and periodic table.